All right, so here's a sample problem where we're going to see how to translate the information given in the problem into these mathematical objects that we need to deal with when solving physics problems, so we can see what's going on. And this problem is a mildly trickier version of a problem that I did right at the very beginning of our discussion of equations of motion for constant acceleration. And this builds in reaction time, which is a more realistic way of looking at the total stopping distance that a car and a driver in it has. So on average, it tells us that the reaction time of a car driver is about 7/10 of a second. And we're saying that the car, when it's braking hard, can have an acceleration that slows it down, so in opposition to its velocity of 4 meters per second squared. And we're asked to compute the total distance covered in coming to a stop. That's an important bit of language. And we're also told that when the driver sees the red light, they're traveling at 23 meters per second. All right, so when you have these problems, probably the first thing that you want to do is to determine what it is that you're trying to find and then try to relate it to some of the things that you're given. And what we're trying to find is the total distance, right? We're supposed to compute that. And we know, if we think about it for a moment, that this is going to have two pieces, right? First, there's going to be that 7/10 of a second where the driver has seen the red light, but hasn't yet been able to apply the brakes, right? That's their reaction time. So their velocity won't be changing, and that means their acceleration will be 0. And so they're going to cover some little bit of time, a little bit of ground during that. I'll call it delta x1. And then they'll also, once they start braking, still be moving forward for some time. And so they'll cover a little bit more. So I'll call that delta x2. And to put this into clearer terms, let's actually draw out what their velocity is doing as a function of time. And for the first 0.7 seconds, they are just still rocketing along at 23 meters per second, which I'm going to call our initial velocity. And then once they hit the brakes, they decelerate at some constant rate. So we have a linear v versus t graph. And their final velocity will be 0 meters per second. Now, we should know at this point that if we try to apply the equations of motion to this entire period of time, that we're going to get things that don't make a lot of sense, because the acceleration changes right at that moment from 0, because the velocity isn't changing for 7/10 of a second, to this negative 4 meters per second squared. Okay. All right. So if we say that our little car is zipping along and it's at initial velocity, and then sometime later it's going to have stopped. So v final is 0 meters per second. Put that there. And we'll say that this direction is positive and this direction is negative. You could flip it. Doesn't actually change anything about the problem except the signs of the numbers that you're going to be putting into your equations, but it still tells you the same thing in the end. Okay. Anyway, we'll say that the initial velocity is to the right, and so their displacements are going to be to the right, and that means that the acceleration that it experiences is going to be to the left, negative, to slow it down from 23 meters per second to 0. Now, how to actually solve this out? Well, we have two mini problems within this one big problem, and I think the easiest part of it is the first part. We know that the average velocity equation is this. And if we think about it, we should realize that this initial velocity is also equal to the average velocity for this first part of its motion up to 7/10 of a second. Why is that? Well, if you take the velocity at any point along here, it's going to be 23 meters per second. And so if you take a whole bunch of samples and you say, okay, it's all 23 meters per second, and then you divide by the number of samples to get the average, you just get back 23 meters per second. So we can use this equation, and we know what the time period is for this to occur. I'll call it delta t1 because it's the period of time for this first part of the car's motion. And then we can solve for delta x here. I'd like to do this symbolically. Just multiply both sides by delta t1. And we know that this is 23 meters per second. We know that the period of time, that reaction time where they haven't changed their velocity yet, is 7/10 of a second. And when we plug all of that in, we get about 16 meters. So that's 16 meters covered before they even really start braking. I think that's pretty clear why we were able to do that. Okay, and we're given that 7/10 of a second, et cetera, et cetera. All right, now for the second part of the motion, well, we don't know the time, and the velocity is changing, so we can't just apply the average velocity equation or something like that. We need to apply one of the other equations of motion that we have. All right. Which one is most appropriate? Well, I mean, there's one that's shorter than the others, though you can certainly go about your business in whatever way you choose, as long as it's consistent. But the shortest route between 2 points here is to use the one that doesn't involve time. Because although we know exactly how much time it takes for this first part of the motion to occur, we actually don't know how long it takes for this second part of the motion to occur. We could go find that out, but we don't know it to start with. So we're going to use the one equation of motion that we have that doesn't involve time. And we'll use delta x2 because we're figuring out the second part of the total distance covered. It's a displacement, but all of the displacements are in the same direction, so we can just add them up to find the distance. Our final velocity is 0, so this side of the equation is going to be nice and simple. And then we just need to solve for delta x. We subtract v0 squared from both sides. We divide both sides by 2a, and that will leave us with just delta x2 on the right. And we can substitute in all of our various quantities here, 23 squared and 2. Remember, this is a negative acceleration. If we don't put in the negative acceleration, we get a delta x that is negative, and that won't make much sense. We don't start moving backwards. We're still moving forward, just slowing down. And when we plug those numbers in, you should get, let's see what I've got. If I've punched it into my calculator correctly, then you get a little over 66 meters. So to get the total distance, we just want to sum up those two numbers. And once we do, and round it to a couple of sig figs, since we've got 2 sig figs in this number up here in the problem statement, we get about 82 meters for the total distance. Circle that, and you're all done. So I hope this was useful in looking at the process one more time for a different kind of problem. But once you get a few more of these under your belt, and I would encourage you to do some of that, right? The assignments are sort of the bare minimum as far as the number of problems of a certain type that I'd like you to do. If you're really preparing for, maybe not the quizzes, but definitely for like the exams, I would go and pick out a few more from the back of the chapter and just give them a whirl. And I'm always happy to answer any and all questions you run into with those, check your work, etc., etc. So, hope you enjoyed. Talk to you later.